regarding decision density. And as I said in the beginning, there are actually a ton of decisions to be made all of the time. In these scenes, you can see we're making up to 100 or so pairwise interaction assessments with actors on the road. If we were driving even on the highway or even in a less dense city or in suburbia, there would be far fewer interactions to consider, but we need to consider on the order of 100 in just a very typical city scene. All of these interactions, we need to understand what our future actions would be, and that's what these 5,000 or so trajectory rollouts are. And we're not just doing this once every minute or so, this is happening 10 to 100 times a second on the vehicle in order to figure out where to drive. So that's challenge one. Challenge two is uncertainty. And uncertainty is actually present in all of the decisions that we're making, not just some. And I use this example on the right to highlight how no amount of modeling precision is actually going to remove uncertainty. That's in fact not our goal here, because as you can tell with these bikers, the one in the front is probably slightly more likely to go to the left, and the one in the back, we really don't know. And infinite modeling precision will never actually account for the inherently uncertain future states of actors like this. So we need to account for this. This is what we call kinematic uncertainty. There's other kinds of uncertainty, existence uncertainty, which we'll talk about a bit, which is the uncertainty of the unknown or what's inside occlusions. And then the last is modeling error, which is a way of saying, how do we account for when the world isn't evolving as we expect? What if one of those bikers turns around or falls over and this is just not captured in one of our models? What do we do in scenarios like that, which we see all of the time, of course, in dense cities where there are tons of bikers? So those are the two challenges. Despite those